Hi guys, Audrey here. So we're going to do a few L'Hopital's rule problems where the indeterminate form in the beginning is infinity over infinity. So let's start with this limit as x approaches infinity of x squared over 2 to the x. When I plug in infinity squared, that's just infinity. 2 to the infinity is also infinity because that's like 2 times 2 times 2 times 2 times 2 times 2 forever, which gets really, really big. So infinity over infinity. So I am allowed to use L'Hopital's rule, HR on top of the equal sign to show that you're using it. And then we do the derivative of the top and the derivative of the bottom. So remember the derivative of an exponential function, it does not change, but then we do times ln of the base. So that's times ln 2. Well, now when I plug in again, 2 times infinity, well, that's still just infinity. 2 to the power of infinity, also still infinity. That ln 2 isn't changing that. That ln 2 is just multiplying it by something to make it bigger. So then we end up with equals 2. We're going to use L'Hopital's rule again. There's really no possibility of simplification here, so it's pretty straightforward. We just apply L'Hopital's rule a second time. Limit as x approaches infinity of 2 over 2 to the x ln 2 squared. Let's just briefly talk about that derivative. What we said is that the derivative of, actually, we'll say the derivative of a to the x is a to the x ln a, which meant that 2 to the x was 2 to the x ln 2. But ln 2 is just a constant. It's just a number, like a 5 or a 7. So I'm going to actually think about this. If I were to do ln 2 times 2 to the x prime, I'm going to move that ln 2 to the front because typically we put constants in the front. So this might help us to think about this thing. So the ln 2 doesn't matter. It's just a constant. So constant, we put it down, and then we multiply by the derivative of 2 to the x, giving us another 2 to the x ln 2. Well, now we have 2 ln 2's, which means I have 2 to the x ln 2 squared. Great. Okay, now when we plug in, we have a 2 on top, but I still have an infinity on the bottom. 2 to the infinity hasn't changed, still infinity. Remember, division by infinity gives us 0. As the bottom gets bigger and bigger and bigger, that means the whole number is getting smaller and smaller and smaller. So this is going to 0, and we are done with this question. So this one was pretty straightforward and simple. We'll do another one that's maybe a little bit more challenging. Okay, we have ln of 4x plus 9 over ln of 7x minus 6 plus 5. We want to plug in. I'm just going to really briefly draw a graph of ln x. So ln x kind of looks like that. So if I'm looking at ln of 4x plus 9 or ln of 7x minus 6, when I plug in, I have like ln of infinity over ln of infinity plus 5. But when we look at ln, at this ln x right here, what's happening to my y values? As my x values go to infinity, those y values we can see are just getting bigger and bigger and bigger. So ln of infinity is just infinity, which means that this is infinity over infinity. So we can apply L'Hopital's rule. So we're going to get equals here with an HR on top. The limit as x approaches infinity of 4 over 4x plus 9 divided by 7 over 7x minus 6. The derivative of 5 is just 0. So the 4 on top is because the derivative of 4x plus 9 is 4. The 7 on top is because the derivative of 7x minus 6 is 7. So remember, for logs, we're applying the chain rule here. The thing on the inside, the 4x plus 9, goes on the bottom, and its derivative goes on the top. So derivative over the thing itself. Derivative over the thing itself. So now, before we plug in again, remember we always want to simplify. I'm going to write equals. I'm going to put a little s here just to show that I'm simplifying. The limit as x approaches infinity, I'm going to write the numerator as a fraction. And remember, division by a fraction is the same thing as multiplication by its reciprocal. So that'll be 7x minus 6 divided by 7. So I'm still just going to continue with this simplification. X goes to infinity, 4 times 7x minus 6 over 7 times 4x plus 9. Now, we have two options. When I plug in, I can do infinity over infinity. I get infinity over infinity. So that means I can apply L'Hopital's rule again. But this limit is approaching infinity. And when the limit's approaching infinity, remember, we can also just take the big things, the dominant terms, take the big stuff, the dominant terms from the top and the bottom. So my dominant term on the top is 4 times 7x. My dominant term on the bottom is 7 times 4x. So this is equal to the limit as x approaches infinity, 4 times 7x over 7 times 4x. And notice everything actually just cancels out, and this equals to 1. So we were able to get that 1 with one application of L'Hopital's rule just by taking the dominant terms, taking the big stuff. But note that we could also have used L'Hopital's rule. So the option of L'Hopital's rule, HR, for a second time. Instead of just taking those dominant terms, I could also take the derivative again. Limit as x approaches infinity, that constant out front's not changing anything, then the derivative of 7x minus 6 is 7. That constant out front's not changing anything, the derivative of 4x plus 9 is 4. And guess what? We see everything here cancels out as well. And we get 1 just in a little bit of a different way. But either way, we end up with that 1 as our final answer. Okay, so we're just going to do one more problem. We're going to do a problem that doesn't have x going to infinity, because I want you guys to see that it doesn't have to be going to infinity for us to end up with the infinity over infinity form. Okay, so limit as x goes to 0 from the right of ln x over x to the negative 1/2. We want to plug in. So I've already done a graph of ln up above, but we can't see it anymore. So we're going to draw it again. This is ln x. Now I want to know what's happening as x approaches 0 from the right. So in other words, I'm letting my x values go to 0, which means what's happening to the y values here? Well, we can see that those y values are getting smaller and smaller and smaller forever. They're just going to keep going down, down, down. So ln x, as x goes to 0 from the right, is negative infinity. Now let's think about 0 to the negative 1/2. What's going on there? Remember, negative exponents mean 1 divided by. So this is actually the same thing as 1 over 0 to the 1/2, which is just going to infinity. I know that it's going to be positive infinity because we said 0 from the right, which means 0 from positive values. So if I were to plug in a positive value, I would get something positive. This is going to infinity. So this is negative infinity over infinity, which means I can apply L'Hopital's rule. So I end up with the limit as x goes to 0 from the right. The derivative of ln x is 1 over x. The derivative down here is negative 1 over 2, x to the negative 3 over 2. Now remember, before we just immediately plug in again, we want to simplify this thing. So I'm going to simplify it by rewriting that x as x to a negative power, so x to the negative 1, x to the negative 3 over 2. That negative 1/2 on the bottom can be moved to the top as a negative 2. I'm just simplifying here. And now I'm going to apply my exponent rule to see that this is the limit as x approaches 0 from the right of negative 2x to the positive 1/2. So what I'm doing there, I'm remembering that x to the a over x to the b is equal to x to the a minus b, which means x to the negative 1 over x to the negative 3 over 2 is equal to x to the minus 1 minus negative 3 over 2, which is x to the minus 1 plus 3 over 2, which is x to the 1/2. Well, now when I plug in, I just get 0. So my final answer here is just 0. And we are done with L'Hopital's rule, infinity over infinity form. Note that this idea of this simplifying the exponents, like we did right here using this exponent rule, shows up quite a bit in the infinity over infinity form. So just be careful about that. That's all. Bye, guys.